Sure. So we talked about colligative properties and what they do when you have non-volatile solutes in volatile solvents. All right, and we're going to pay attention to these four things that it affects: vapor pressure, boiling point, freezing point, and osmotic pressure, but mostly the top three. And keep in mind which direction it modifies them. All right, we talked about Raoult's law, and we showed mathematically why it is that the boiling point is elevated. It's because the vapor pressure gets lowered. Those two are actually tied together. Raoult's law shows us mathematically why it is that the vapor pressure gets lowered when we add non-volatile particles. And because it gets lowered, that means you need more energy to that liquid to get the vapor pressure, the lower vapor pressure, to now match the atmospheric pressure above the liquid, because you've now learned that's the definition of boiling point. When the vapor pressure is equal to the atmospheric pressure coming down on the liquid. Okay? So those two are tied hand in hand. But then we ended with just kind of thinking about empirically why it is or how it could be that by adding non-volatile particles to a solution, you actually increase the boiling point. And the idea is just that you're making a physical barrier for those molecules to escape into the atmosphere. And then we ended with using that same concept, those same barriers, preventing, in this case, water molecules from condensing into the solid phase. So it was a barrier for them to come together. It's not a barrier for the solid to melt back into a liquid. That's just fine. So where they were in equilibrium, they're now not in equilibrium because this reaction, going from solid to liquid, is unchanged by adding non-volatile particles, but it slows down or impedes or is a barrier to the liquid condensing into the solid. So you have to get things that much colder to get those arrows to match up again. All right? And I'm going to leave it at that. We're just going to think about that one. There's no equations that we need to get into that explains all that. We're actually going to be calculating what those changes in temperature are with some equations in a little bit. But before we do that, we need to talk about a few other things. So here's the phase diagram, and all the points of interest, all right, are listed for you on here. Here's the normal boiling point. It's on this part of the curve here. And when we add non-volatile particles, we increase the boiling point because we've lowered the vapor pressure. You can see that here. Here's the boiling point of an aqueous solution. That's when you've got non-volatile particles dissolved in them. So we increase the boiling point. So at the same pressure, 1 atmosphere, we need to get the solution hotter before it boils. So any place on this curve, anywhere we are on the pure water curve, we're increasing the boiling point when we have particles in solution, okay? And for the freezing point, here's the normal freezing point of pure water. So again, this line here is going to be of pure water. And this line here is going to be, again, our aqueous solution. We're lowering the boiling, the freezing point. Okay? I'm just showing you what we've been talking about, but overlaying it on this graph that you've seen before. So effectively what we're doing is what's written up on top here. We're increasing the overall range that the solvent remains in the liquid phase because we're increasing the boiling point, which means it stays liquid at higher temperatures, and we're decreasing the freezing point, which means that we're on the lower side. We're also increasing the temperature range at which a material stays in the liquid phase. So if blue is liquid here, okay, then now we've got, with colligative properties, right, we've got a much larger region in blue. We've increased the liquid range. And I don't really need to show you that any other way, I think. I think this figure gets the point across pretty easily. But this is going to be true of all solutions. All right, now, this has all been qualitative. All right, you need to know what effect non-volatile particles have with respect to those four variables. Right? Vapor pressure, boiling point goes up, freezing point goes down, osmotic pressure goes up, vapor pressure goes down. But also understand what's going on empirically that causes that. But now we're going to get quantitative, and we're going to start calculating what those changes actually are. And for us to be quantitative, let me just show you what the general relationship is. We're going to calculate the change in temperature. So you'll remember the triangle, what the triangle is. It's a capital Greek D, delta, for change. The change in temperature is going to be dictated by some proportionality constant that's going to be unique for whatever the solvent is. And that's just going to be given to us. And then the concentration of non-volatile particles in the solution. Okay? And it's really that simple, equation-wise. Actually, it's going to get a little more complicated in just a moment. The proportionality constant, let me just it's going to look something like this. It's going to be, it will change so many degrees Celsius per particles in solution. So if I know that there are 10 particles in solution, and every 10 particles of solution, the temperature changes by 1 degree Celsius, that's what the proportionality is. How much it changes in temperature will be completely dependent on how that solution responds to non-volatile particles. That's why it's going to be unique for every one that we're working with. But the concentration, to really do this well, we need to understand something new to probably all of you. Because what does that capital M represent? What do you know that capital M for? Molarity. And what is molarity?
Moles per liter.
Moles per liter, okay? Well, we can't do that. So we're not going to be using molarity. We're going to be using something new. Two new things we're going to be using. One is we're going to be using something called molality, not molarity, and you'll see the difference in a minute. And we're going to be talking about something called the Van 't Hoff factor, which will also tell us how many particles of non-volatile things are in the solution. So these are the two new things. We're going to be discussing these today. We probably will get done with it today. So let's get right into it, shall we? Without further ado, molality. Here is your general definition of what molality is. It's very similar to molarity. Okay? As the definition goes, it's simply the moles of solute per kilogram of solvent. So it's by the mass of the solvent, not by the volume of the solvent. And the reason we care about this is right here. Volumes will change with temperature. And what are we doing with boiling point elevation and freezing point depression? We're changing the temperature. Okay? So if I started with 1 liter of solvent at 25 degrees Celsius and I raise that up to 100 degrees Celsius, it's no longer 1 liter. All right? It's actually gotten larger. The volume actually changes with temperature. So we can't use molarity, we need to use molality, because it keeps, now we already learned about mole fractions. It keeps them unchanging. So let me show you that by example. But before I do that, let me just write down a few more notes here for you. Right? We use this for colligative properties. Because the molarity changes with temperature. Now, for an example, here's molarity, as we know, capital M. It's the moles of solute, so N is moles, okay, per liter of solution. So let's say I have a 1 molar solution of NaCl, okay? So 1 molar NaCl. So I can, by molarity, that's going to be 1 mole of NaCl per 1 liter of solution. And let's say I have this at 20 degrees. Okay? And now I take a look at the same solution. If I have 1 mole of NaCl at, if I have the same solution at 90 degrees, for example, as I just said, the volume increases. So now we're going to have more than 1 liter. Okay? Let's just do it this way so we don't get our greater than and less than signs confused. We're going to have greater than 1 liter at 90 degrees. So overall, is the molarity going to be higher or lower at 90 degrees than it was at 20 degrees? It's going to be higher. Who thinks it's going to be higher? Who thinks it's going to be lower? It's going to be lower, right? Because the denominator now is larger. So in this case, we have 1 molar at 20 degrees, and now we have less than 1 molar, or yeah, less than 1 molar at 90 degrees. Now if we do it by molality, right, if I have 1 mole of NaCl per 1 kilogram of solvent. Now why kilogram of solvent? What's the density of water under standard temperature and pressure?
1 gram per milliliter?
Density of water, does everyone agree or disagree? Agreed, right? Density of water at standard temperature and pressure is going to be 1 gram per milliliter. Now we want kilograms, not grams. So we multiply by 1,000. We also want liters because I want to make a comparison to molarity, which is per liter. Well, so they're both multiplied by 1,000. So that's the same as 1 kilogram per liter. All right? So that's why it's per kilogram of solvent, because I want 1 liter of the solution. Well, the analogy here, if it's 1 liter, we have 1 kilogram of solvent, using water as our baseline here. Okay, everyone with me still? Good. So if we have that at 20 degrees, and I raise it to 90 degrees Celsius, well, I'm still going to have my 1 mole of NaCl, and I'm still going to have 1 kilogram of solvent, because the mass doesn't change with temperature, only the volume changes with temperature. So now we're going to have 1, now it's molal, so we use a lowercase m, it's still 1 molal at both temperatures. So over here for molarity, where we would call this a 1 molar solution, if it's molality, we call it a 1 molal solution. You don't hear much about molality, do you, these days? It's really in this realm that we care about it, and as you'll see through a couple of examples, the difference isn't that much, okay? But it is measurable, okay? And when people are really studying colligative properties like this, you need to use molality or else you will get a slightly different answer, right? And that's why we care about this. So, speaking of examples, this is an example out of your textbook within the chapter. Now, one thing I can't stand about this textbook, might be recorded, is that here we are in Gen Chem 2, all right? in the middle of the textbook, and they're still giving you problems in pounds and quarts and asking you to convert it into metric. Which, don't worry, folks. I'm not going to ask you to convert from the old English system to the metric system that everybody on this planet should be using anyway. And especially in science, we are a metric. So I already went ahead and did those conversions for you. That also makes this problem a little trivial. But we always start with the easy ones, okay? If you're not given what the density is, or if you're not given the conditions, you can assume that you're at standard temperature and pressure, where we've got the density of water is 1 gram per milliliter. It's okay to assume that, unless you're told otherwise. What was your answer?
Just 7 molal.
Let's just write this down. 1.37 molal. What did you get?
1.37.
1.37. Anyone else get 1.37? Anyone get something different from 1.37? I also got 1.37 molal. So congratulations. Now for everyone else, let's go ahead and run through this. So we know what the definition of molality is. We need the moles of solute and we need the kilograms of solvent. Now I told you to assume this. That's going to be the same as 1 kilogram per liter. All right, so usually your reported density is in grams per milliliter, so get used to it. All right, it's a factor of 1,000 for both sets of units, so the number is the same. All right, we need moles of solid, but we're given grams. So 226.80 grams of sodium chloride. We need to get that into moles. And if I've told you this before, I don't care. I'm going to tell you again. A lot of you just try to remember, oh, when I go from grams to moles, I multiply. When I go from moles to grams, I divide, whatever. Do it by dimensional analysis, and you never have to remember it that way, because if you just try to remember it, you're almost guaranteed to forget it on an exam. So that's why dimensional analysis is so beautiful, all right? We're going to have grams down here. We're going to have moles up here. The molar mass in grams, all right? It's going to be the inverse of the molar mass. So we add these two up from the periodic table, and you should get whatever it is, 58.44. Say one thing and I write another. 58.44 grams per mole. That gives us how many moles? Always bring your calculator to class, all right? That gets you in the habit of using it and not your phone, because I won't let you use your phone on an exam. 226.8 divided by 58.44 gives us 3.88 moles of NaCl. Okay? Now we need the kilograms of solvent. Well, we're given 2.84 liters, and we know that it's, again, this is just dimensional analysis, but I'll be thorough. 2.84 liters of water, and it has a density of 1 kilogram per liter. So that's going to give us 2.84 kilograms of solvent, H2O. And now we can calculate the molality. It's 3.88 divided by 2.84. Rounds to 1.37 molal. Okay? So this one was very straightforward. It wasn't really a trick. The only extra step was that we needed to convert grams into moles. Okay? This next one, though, is not straightforward, and I'm just going to take you through it. When you're reading along in the textbook, it takes you through this example, and it's a good example, okay? And it's good to keep in mind, but this is not straightforward. So let me just lead you through this one. The reason this one's tricky is because we're given the molarity, and we're asked to calculate what the molality is from that. And the reason it's tricky is because we have to figure out the mass of the solvent, but it's embedded in this solution. We're already starting with an aqueous solution. We need to figure out what the mass of the solvent was in that aqueous solution. Okay? Now we're given the density of that aqueous solution. The density is that grams per milliliter, which of course we know is the same as 1.022 kilograms per liter as well. Although I don't know if we're going to need that here. Yeah, question.
What is this? Is CA?
Ca. Anyone know what this is? This is Latin for, it's approximately. Circa, approximately.
Oh.
It's Latin.
Tilde.
The same as the little tilde sign. Yeah. The little squiggle. Yeah, okay, let's put that in. That's what Ca is. Now, we're not told what volume of this liquid to use. So sometimes in a problem like this, you have to be creative. That's the other reason I wanted to lead you through this one. You're not given a volume, but you're given a molarity. So that molarity is the same regardless of what volume we use. So to make it easy on yourself, let's work with 1 liter. Okay? This problem works no matter what volume you use. So we're going to take 1 liter of solution. Now, 1 liter of solution, we can get that right into kilograms, I suppose, if we wanted to. But for a reason you'll see in a moment, I actually want to put this in grams, not kilograms. Let's just turn this into milliliters. I want grams per milliliter. I want to use this density right here. So how many milliliters in a liter? 1,000. So this is 1,000 milliliters of solution. And the density of that solution, it is 1.022 grams per milliliter. That's going to give me the mass of the solution, which, because we're working with 1, that's easy, right? That's 1,022 grams of solution. Okay? Now I want the mass of the solvent. I don't want the mass of the solution. But we also know how many moles of salt are dissolved for every liter. That's what the molarity tells us, right? So how many moles of NaCl are there in 1 liter? .58, right? 0.558, yes. So we've got 0.558 moles of NaCl per liter. Well, what's the mass of that? Well, we know the mass of NaCl, right? We just did that. So that's now we need moles in the denominator and grams in the numerator. 58.44 grams per mole. Now I'll know how many grams of salt there was in that solution. So that's 0.558 times 58.44. So that's 32.6 grams of NaCl. Now I can figure out what the mass of the solvent was, because we take the total mass and we subtract the mass of the solute, right? And I get 989.4 grams of solvent. Right? That's why in that video, right, know what the solution is, know what the solute is, and know what the solvent is. Because we use these terms all the time. Okay, now we can finally get to the molality. Because molality is the moles of the solute. So in 1 liter, we have 0.558 moles of NaCl. Remember, this is all in 1 liter. Okay? And in that 1 liter, what's the mass of the solvent in kilograms? Just have to convert it from grams to kilograms. And now we can calculate the molality. And I get 0.564 molal. Not too much different from the molarity. That's what I told you at the beginning. But it is different. It's not an insignificant difference, even though it's a small difference. But that's why. Okay? So again, this was a harder calculation. So now that you've got it in your notes and you've seen me explain it, this is a great type of question for practicing that new study technique that I've been telling you about. So when you go home tonight to study, right, take this same problem, but don't look at the solution, and see if you can recreate this in a way like you're lecturing it to somebody. Or if you have study buddies, do it back and forth with each other. If you can explain how to do a problem like this, right, then you really understand what's going on. You can piece these things apart. All right. So that's what molality is. You should know what it is. You know how to calculate it. Know what the difference is. Now let's talk about that other new thing that you need to know about, which is the Van 't Hoff factor. And this has to do with counting the number of non-volatile particles in the solution. And what's important here is that all we care about is the number. It doesn't matter what they are. It just matters how many there are. So this is going to be independent of the identity. Not the identity. Just the number. And it's the number of non-volatile particles. Because those are the ones that are getting in the way. Those are the ones that are either reducing the vapor pressure if we plug it into Raoult's law, or are just causing that barrier that we talked about empirically. And really what this boils down to, sorry, no pun intended, what this boils down to is the difference between something dissolving in solution and dissociating further into its component ions in solution. It's something that you should have learned in Gen Chem 1, but I'll give you a quick review now. So this is dissolving versus dissociating. And I'll just add to that, dissociating further into its component ions. That really, in this case, it's ions, because we're talking about the difference between something that's an electrolyte and something that's a non-electrolyte. Simply put, when things dissolve, they both dissolve in solution, and when they dissolve, it looks like it disappears, right? But an electrolyte, when it dissolves in aqueous solution, it further dissociates into its component ions. Whereas an electrolyte stays as whatever it was. Typically, that's going to be a covalently bonded molecule. So non-electrolytes, covalently bonded molecules, they don't dissociate further. So the classic example we like to use for this is glucose. So if I take C6H12O6, that's glucose for all of you biology majors out there. Okay. And if I take 1 mole of glucose, solid, and I put it in water, it will dissolve. Okay, it's not table sugar, but it's like table sugar. That's sucrose. Okay, but glucose, you put it in water, it's going to dissolve. But when it dissolves into 1 mole of glucose. Here, let's be specific. Whoa. 1 mole of C6H12O6. Now, what's the phase? Is it solid? What is it? It's aqueous. But it's still 1 mole. So if I take 1 mole of solid particles and I dissolve it into solution, if it's a non-electrolyte, I'm going to still have 1 mole of particles in solution. Whereas electrolytes, if I say take, let's see, what should we use? Let's use calcium chloride. What's the molecular formula for calcium chloride? Calcium, Ca, chloride, Cl. What else? Remember, we got to balance the charges.
CaCl2.
CaCl2. That's right. So if I take calcium chloride, let's take 1 mole of calcium chloride and let's put that in water. What are we going to get? What happens to an ionic compound that's soluble? Okay, what? It break apart. Now you do need to make sure that it's soluble, and you do have solubility guidelines. They're at the front of the slide pack here. I talk about this briefly in the video. This is also Gen Chem 1, right? This is going to be for things that are generally completely soluble in water. And you know that calcium chloride is soluble in water because you've got any compounds that contain a chloride as the anion will be soluble unless the cation is one of these. And that doesn't include calcium. So calcium chloride is soluble. All right. So this is going to dissociate into its component ion. So we're going to get calcium 2+ ion in aqueous solution. What else?
Two chlorides.
Say that louder?
2 chlorides.
2 chlorides. Okay, don't write this down. All right, I'm about to show you the wrong answer. One of the most common mistakes students make in this kind of an analysis is they're going to write this. Don't put this in your notes. This is wrong. Okay? Don't be that student that gets this wrong. It's Gen Chem 2 now, all right? Chlorine gas, Cl2, that's how chlorine exists in nature. This is an aqueous solution. Okay? This is going to be 2 Cl- in aqueous solution. So for every 1 mole of calcium chloride that dissociates, it dissociates into 1 mole of calcium ions and 2 moles of chloride ions. So if the Van 't Hoff factor is looking at the number of volatile particles, regardless of what they are, what's the molarity of particles in solution? Is it 1 molar, 2 molar, or 3 molar? Here, just show up your hands, 1, 2, or 3. All right, I have 1 mole of this compound, let's say solid, okay, I didn't put a solid on there. And now it's dissociating into how many pieces does this fall apart into? 1 mole of this and 2 moles of that. So if I started with 1 mole of calcium chloride, I have 3 moles of particles in solution. 3 is the right answer. And since it's the particles in solution, that's what dictates the colligative property. That's what's going to dictate how much is the temperature going to rise if it's boiling point elevation, or how much the temperature is going to lower if we're measuring the freezing point depression, or how much the vapor pressure is going to change, or how much the osmotic pressure is going to change. We need to know how many moles of particles there are in solution, independent of what those particles are. Another common mistake that students make is when they're putting glucose, a molecule, all right? The reason this falls apart and this doesn't has everything to do with what we talked about in Gen Chem 1. When you pour sodium chloride into solution, all right, it's going to separate into its component ions due to stronger intermolecular attractive forces between the water molecules and the ions than the electrostatic attraction of the positive cation and the negative anion. So that's why covalent bonds don't break when things get solubilized. What's happening is we've got some other stuff going on and the glucose is being solubilized. It doesn't break into 24 different pieces. So it's another common mistake that students make. If you're given a non-electrolyte, by definition, it's not going to break apart into different pieces. And glucose, you should know, is, because I use it all the time. Everybody uses glucose, right? This C6H12O6 does not break into 24 pieces when you put it in water. So don't be that student, okay? Let's emphasize particles. These are non-volatile particles. That's what's having the effect. So we can say that there's an ideal Van 't Hoff factor. That's all this next figure is showing you. There's a theoretical and there's experimental, because not everything's perfect. If I put sodium chloride, we did this with sodium chloride, if I have 1 mole of sodium chloride and I put that in water, how many moles of non-volatile particles should I get? 2. You do need to know your ionic compounds, okay? But again, this is Gen Chem 2, so I would expect you can all recognize that. So this is what we call the Van 't Hoff factor. The I, that's what we use for Van 't Hoff factor. I is equal to 2 in this case. For calcium chloride, I is equal to 3. For glucose, I is equal to 1. And we're going to use that as a simple multiplier. But if you take a look at this table here, that's ideal versus theoretical. So look at sodium chloride. The ideal Van 't Hoff factor is 2 because we know that it breaks apart into 2 ions. But in reality, right, there's some other interactions, there's always some other intermolecular attractive forces going on between the solute and the solvent. So it's not perfect. It's not a perfect 2.0. We can measure it as 1.9. Here's calcium chloride, right? Our theoretical was 3, but when you actually measure it, it's a little less than 3. Most of the stuff that we're going to be doing in this class, we're just going to use the theoretical. Unless there's 1 or 2 questions you might come across where you're asked to actually calculate the experimental, and we can do that in the sense of understanding how these equations work. I think I've already told you this before, but I'll say it again. When we learn how to use a formula or an equation, right, we first learn it the straightforward plug and chug way. But once you understand how it works, you should be able to work it backwards, forwards, upside down, sideways, and diagonally. It's just a matter of where the variables are and what's unknown. You might need to do a little bit of algebra, okay? All right, so let's practice. Let me just remind you, the first 2 we've already done. So if I have 1 mole of glucose and I put it in H2O, I'm going to end up with 1 mole of glucose in aqueous solution. That's going to give me 1 mole of particles in solution. Now, let's make a little chart here, okay? I'm going to put on the right-hand side here, let's also list down what the molality will be. Molality, and we're going to put this in 1 kilogram of solvent. Okay, so here's a new heading here. So 1 mole of particles in 1 kilogram of solvent gives me a 1 molal solution. All right, ethylene glycol. Even though you're not given the chemical formula for it, I use it as an example in lots of things. It's antifreeze, okay? So this is also a non-electrolyte. Now don't worry, on an exam, I would just tell you, it's a non-electrolyte, okay? But you don't always take my exam, so watch out for these things, okay? Ethylene glycol, it's a covalent molecule. It's a non-electrolyte, so 1 mole of ethylene glycol. Actually here, let's make it a little more challenging. Let's give you 3 moles. 3 moles of ethylene glycol in H2O. In aqueous solution, it dissolves, but it gives you 3 moles of particles. In solution, it gives you a 3 molal solution. Okay? Now, that gets you going. I want you to fill in the rest of this yourselves. Well, not yourselves. Work within your island groups, between islands if you need to, okay? And I want you to figure out, here, let me set you up here. Let's say for NaCl, I'll give you 1 mole of NaCl, and I'll give you 3 moles of calcium chloride, and I'll give you 5 moles of sodium phosphate. All right? I want you to fill in the 2 columns here on the right-hand side. Let me change a definition here for you real quick, because I've just realized
I even save the numbers up there.
in helping you that it might be a little confusing because it's the molality is of the compound. Let's just change this into concentration of particles, because I want to know what the concentration of the particles is. The molality refers to the starting compound before it dissociates into its components. So I wanted to make sure we're clear on that. All right, are we ready to solve it together? Okay. It's a little confusing at first, but that's why we're doing it this way. So we've got two things to think about. We need the I factor, the Van 't Hoff factor, and then we'll apply that to the starting concentration of the compound. So the I for sodium chloride is 2. We already looked at that one. So if I start with 1 mole of sodium chloride, it's going to fall apart into 2 moles of particles in solution. So that's going to give me 2 moles of particles, and that would give me basically a really that last column is really redundant, isn't it? I don't really need to put that in. That's okay. It's mostly the moles of particles in solution that we're going for here. What's the I factor for calcium chloride? Say it louder. 3. So if I have a 3 molar solution of calcium chloride, how many moles of particles will I have in solution? I have 9 moles of particles in solution. If I have 5 moles of sodium phosphate, how many moles of particles will I have in solution? It'll be 20. That's right. Because the I factor here is 4. And you can see it right here. Every 1 mole of sodium phosphate dissociates into 3 moles of sodium ions and 1 mole of phosphate ions. And what if I gave you, here let's add one more. Let's say I give you 20 moles of glucose. How many moles of particles do I have in solution?
20.
It says it's 20. Good. It's 20. It's not 20 times 24, which would be, what, 480? All right, yes, this gives us 20 moles of particles as well. So don't be fooled by glucose, okay? It's a covalently bonded molecule. All right, so good. That was a little fun exercise. Now let's apply that idea. Actually, before we go to the next one, this isn't in your textbook, and I wouldn't test you on this, but you may come across this term somewhere down the road. What we're talking about here, what I was getting at this last column, it's the osmolarity. Sometimes it's called the osmolality. That's specific to the concentration of particles in solution. This last column really is the osmolarity. Sometimes that's called the osmolality. It's simply the concentration of particles in the solution, which is ultimately what's going to dictate our colligative properties. But again, that's an FYI. We don't test you on that in this class. It's not in your textbook, so don't worry about it. Okay, so now let's apply this to some actual computations. I think I showed you this same setup, but now it's broken up a little bit more. So we're going to calculate the change in temperature. Sub F is if the freezing point is being lowered, and the sub B is if the boiling point is being elevated. But ultimately, the equation is all the same. We have K, which is your proportionality. It's a proportionality constant. And then we have your Van 't Hoff factor. There's a space there, Van 't Hoff. And then we have M, which is the molality. Now, just so you don't get confused, that's the starting molality. So in the earlier exercise, that would be the molality of calcium chloride, for example. All right, you have, what was that example? You have 3 moles of calcium chloride per kilogram. So you have the molality there. Then you'd multiply that by the Van 't Hoff factor 3 to give you what I just defined as the osmolarity. So again, here I'm going over something that I say is just for your information, but I times M, right? That's your osmolarity. You'll see that in the equation here. Now T sub F and T sub B, that's going to be unique for any material that we look at. Okay, these are unique to each substance, and you would either be given those values, or maybe the problem will ask you to calculate it. It's okay, because we're going to learn how to use this very simple equation, and once you know how to plug and chug it as written, then you'll know how to do anything with this equation by just algebraically manipulating it to solve for another variable, right? You know how to solve everything that I show you, forwards, backwards, sideways, diagonally, and upside down. Okay, so let's do an example here for water. Okay, for H2O, which is what we commonly use, but you'll see some others in the problems in the homework set. K sub F for water, this is what it looks like. Okay, it's 1.86 degrees Celsius per molal. And the way we interpret this is for every molal of the solution, okay, the temperature is going to change by 1.86 degrees Celsius. That is specific to when you're going from the liquid into the solid. Whereas if we take the same amount of water, but we want to see what effect those non-volatile particles will have on raising the boiling point, it's different. It's 0.52 degrees Celsius per molal. So for the same concentration of particles in solution, it has a different effect if that liquid's going into the gas phase versus that liquid going into the solid phase. And that just has everything to do with the properties of the solution. We don't need to get into the physics of it, okay? The point is that it takes a different amount, different constraints dictate liquid going into the gas phase versus the liquid going into the solid phase. And that's why these numbers are different. But we're going to use these values in our calculations. So here's some simple calculations. Let's say we have an 18 molal solution of antifreeze. That's your ethylene glycol. Okay? So let's calculate the boiling point and freezing point of a 1 liter solution of 18 molal antifreeze. Now, antifreeze, this is going to be in water, okay? So we want the new boiling point and the new freezing point, because we know what it is for water. What's the normal boiling point for water? 100 degrees Celsius. And what's the normal freezing point for water? 0 degrees Celsius. So that's our starting point. We're going to calculate the delta, and then from that delta we can figure out what the new boiling point and the new freezing point is. Delta T of freezing point, that's going to be equal to the proportionality constant for freezing point depression for water. I just gave that to you. It's 1.86 degrees Celsius for every 1 molal of the solution. We're going to multiply that by the Van 't Hoff factor for antifreeze. What is it? It's not 18. What's the Van 't Hoff factor for ethylene glycol? It's 1. All right. Now, if this were an exam, I would say this is a non-electrolyte. Okay? So I is 1. Okay? And what's the M? What's the molality? That's 18 molal. You can see how units cancel out. And we're left with the units of degrees Celsius, which is what we want to calculate. 33.5, I'll round this to 1 decimal here. That's degrees Celsius. That's the change in freezing point. So what's the new freezing point? Negative 33.5 degrees Celsius. Isn't that nice? If you put an 18 molal solution of antifreeze into your car's radiator, it's not going to freeze until you get to negative 33.5 degrees Celsius. That's why antifreeze is so convenient. All right, let's do the boiling point elevation. Delta T sub B. Now we have a different K. That's going to be 0.52 degrees Celsius per molal. Van 't Hoff factor is still 1. We're still at 18 molal solution. So that gives us 9.36, 9.4. So what's the new boiling point? Say it louder.
109.4.
109.4 degrees Celsius. All right. Now, a common error that I see students make on exams, if you were to see an equation like this on an exam, make sure you answer the question being asked, because this is asking for the new boiling point. It's not asking for the change. Don't just stop with calculating 9.4. This is not the right answer for the question being posed. You need to add that to the normal boiling point to get what the new boiling point will be. This one, we're asked to actually find the actual Van 't Hoff factor, not the theoretical one. We've been working with theoretical, and I told you for most of this class, we're just going to use the theoretical. But this is a problem in calculating what the actual one is, but it's using exactly the same mechanics. So go ahead and try this one. All right, there's been a little bit more discussion. Now let's see a raise of hands. Who's confident of their answer? 1.86. Keep your hand raised if you got 1.86. Yay! Yes, 1.86. And by the way, you could have seen it right here on the 1.9. It's circled in red, but it's all right. I want to see the calculation. I don't care so much about the right answer. I care about you knowing how to get the right answer. So let's just go through this one real quick. All right, we're using the same calculation, delta T sub F. But now in this case, you're already given what the delta T is. You're told that you're told that the new freezing point is minus 6.57. But from that, we know what delta T is. Delta T is just 6.57 degrees Celsius, right? It's just backwards from what we did. Now, this is going to be equal to the K sub F, which is 1.86 degrees Celsius divided by molal, times the I factor, this is X. This is what we're trying to solve for, multiplied by the molality of the solution. And we're told that. Where is it? Right here. 1.90 molal solution. So now we just solve for X. It's really not that hard. X is equal to 6.57 degrees Celsius times, now I'm bringing the K sub F to the other side, so I'll just do the inverse of that. Molal per 1.86 degrees Celsius. And now the molality is bringing over to the other side, so it's the inverse of molality, 1.90. If I did that right, units should cancel out. Molal with molal, degrees Celsius with degrees Celsius. I'm out of units. But that's okay, because the Van 't Hoff factor doesn't have any units. It's just a number, okay? So, always, when you do dimensional analysis, always keep your units in, because then you know you're on the right track. If you set it up correctly, your units all cancel out, you're good to go. All right, what's the answer here? Oh yeah, your guys already said 1.86. That's what I is, and it's unitless. Okay, good. Good job, everybody. Let's do this last one. Now this one has some fancy words in it, like icosine, and you're told of icosine, but there's a lot to read here. But let's just highlight the key words that we're looking for here. Non-electrolyte. So what's our I factor? 1. I equals 1. What else do we know in here? Blah, 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 what it does. Now the empirical formula, Ch2. Now who remembers doing this in Gen Chem 1? You can calculate, you can calculate the empirical formula, and that's different from the molecular formula. The empirical formula is just the mass of the lowest whole number ratio of the elements in the compound. Right? Now, we don't need to be able to do that to solve this problem, but it's part of the problem. So in the end, we'll do that as well. But let's get to the core of this problem here. We are told that the freezing point is lowered by 1.75 degrees Celsius than the freezing point of pure benzene. We don't need to know what the freezing point of pure benzene is, because we're told what delta T is. This is delta T sub F. And we're told the K sub F for benzene. So we're good, right? Let's now plug in what we know. We've got delta T sub F is equal to 1.75 degrees Celsius. That's how much it changed by. And that's equal to K sub F, which is 4.90 degrees Celsius per molal, times the Van 't Hoff factor, which is 1, because it's a non-electrolyte, multiplied by, now here's the unknown, okay? We don't know, because we're asked for the molar mass of icosine. Really, what we can solve for here is the molality. Let's just keep the molality as the unknown. So I think it's a little easier to see it this way. Because right now we can solve for M, right? M is equal to 1.75 degrees Celsius times molality, one molal divided by 4.90 degrees Celsius. Oh, that's it. Degree C cancels with degree C, and we have the molality. Well, that was easy. That gives me 0.357 molal. Now I said, flippantly, I said earlier, yeah, just round it to 1 or 2 sig figs. Do that at the end. When you're in the middle of a calculation, my rule of thumb is to always carry 1 or 2 more sig figs than you think you need in the end, because you don't want a wrong answer just due to early rounding error. So I always will carry an extra sig fig or 2, whether I need it or not. Okay, so that's the molality. But what is the molality? That's going to be the moles solute divided by kilograms of solvent, right? So, what is the kilograms of solvent? How many kilograms of solvent do we have? That's the mass. So how many kilograms is that? It's 1 gram. It's only 1 gram of benzene. That's not much. I don't know why they chose it for this problem, but so what is that in kilograms? Okay, if you don't know it, do dimensional analysis, all right? Because no one's blurting it out except for you, all right? Let's just do it by dimensional analysis. You got 1 gram, and I want that in kilograms, and I know that there's 1,000 grams in 1 kilogram, so now I know that it's 10 to the minus 3 kilograms, all right? Don't be afraid to just scribble out a little dimensional analysis to save your life on an exam, okay? So that's the mass of the solvent. What's the moles of solute? We don't know what that is, right? But now we can solve for it. Moles of solute. This is the icosine, right? That's equal to 0.357. So now we can calculate moles, right? Moles of solute is equal to 0.357 molal times, looks like it's times 10 to the minus 3 kilograms. Now the units actually do cancel out because molality, remember, is moles per kilogram, right? So the units do cancel out. I don't want to trick you here. This is moles per kilogram. So the units will cancel out to give us moles, which is what we want. I don't need to put this in my calculator. Clearly this is going to be 0.357 times 10 to the minus third, which is the same as 3.57 times, let's see, I'm making that bigger, so I make this smaller, 10 to the minus fourth. We're almost there. So we have moles. This is moles of solute, and we want the molar mass. Well, are we told what? Yeah, we are told how much mass of the solute we have, 100 milligrams. So now we have the molar mass. Here, I'll put it in red. We want this in grams per mole. We have moles, 100 milligrams, that's 0.1 grams, and we have 3.57 times 10 to the minus fourth moles. That's your molar mass, grams per mole. 280 grams per mole. That's the molar mass. Now, most of you have already heard of the term osmosis, but I'm going to start with just diffusion, because diffusion is a real easy thing to understand. Things tend to want to be more stable. If they're more concentrated and they're given the opportunity, they're going to want to become less concentrated. If you start at a high point and you have the ability to go to a lower area, you're going to do that, right? Things want to go to their most stable, less energetic state as possible. So we can call this a concentration gradient. And in a concentration gradient, you want to tend to go, well, you don't want to, you just will. If you're in a high concentration and you're able to, you're going to go to a low concentration. And sometimes we call that something going down its concentration gradient, if you've ever heard that term. That's what it means. You're flowing down a concentration gradient. And that's the definition for diffusion here. It's the net movement of solute or solvent molecules from a high concentration to a low concentration. When we get to thermodynamics, there's an entropy explanation for that, but we're not there yet. Now, osmosis is simply the diffusion of the solvent where water is the solvent. And we observe it when we have solvent particles that are flowing across what's called a semi-permeable membrane, which is just a fancy term for a selective membrane, right? What does that really mean? Selective to what? What it means is that solvent can pass freely across the membrane, but not all solids. Okay, that's what that little dashed line is. So on the left-hand side, let's just put some water in here. Now, semi-permeable, so the solvent, the water, that can go on both sides of the membrane. It flows back and forth, no problem. So I'm just going to put 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll put 10 water molecules here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 water molecules here. So if I were to use this as a concentration of water on one side or the other, I've got 10 molecules of water over here, and I have 10 molecules of water over here. All right, it's even. If I started with 8 and 12, well, the water can pass freely. All right, so eventually we're going to get to 10 and 10 here. Now, what happens if I put some solid in here? I'm going to take some red particles and I'm going to put them over here. Let's say I put 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what do we have here? Let's see. Solid. On the left-hand side, there's 0 solid. And on the right-hand side, we have 10 solid particles. By the way, this solid can't pass the membrane, all right? It's semi-permeable. So think of it as just something large. So the solid stays on the right. So now let's just treat this as a simple concentration. What's the concentration of water now? On the left-hand side of this compartment, we've got 100% water. And on the right-hand side, obviously, we only have 50% water. So if we just think about the concentration of water, water is a high concentration here on the left, and it's a low concentration here on the right. So water is going to flow down its concentration gradient. It's going to diffuse from the high concentration to the low concentration. So we're going to get this situation. Remember, those red particles couldn't pass through the membrane. So they're still there. But the water molecules, they can pass freely, and they, by this description, they're flowing down their concentration gradient. So now we're going to have fewer on this side and more on this side. All right, so the water here is flowing from high to low concentration. Now, that's the description of water diffusing. Osmosis is the same thing, but it's describing the direction of water flow relative to the solid concentration. And that's why osmosis as a definition is usually confusing to people. So let me just show you both of them right here. If we're defining osmosis, here we have the water is flowing from an area of low solid concentration to high solid concentration. It's just the opposite. It's the same thing. We're just defining it relative to the solid, rather than relative to itself. This doesn't go to completion. You might think, well, why doesn't all the water continue to go across this membrane so that we have nothing on the left-hand side and everything now is on the right-hand side? And the reason for that is we have some pressure above this surface. pushing down on it, okay? And if we think about the pressure that's pushing down on it, in the starting condition here, we have the same pressure pushing down right on here, and the pressure is not changing. So we still have the same pressure pushing down in all these cases. But at some point, we've got another force. Whoops. We have another force at play here. Because now we've got this pressure of the water flowing due to osmosis. Before we had those red particles in there, everything was equalized, and the levels on both sides of the compartment were the same because there was no net flow, and the only pressure was the same coming down on the surface. But now we have a pressure of net flow going from the left to the right-hand side, and it stops because at some point there's going to be a balance between that flow and the pressure from above the solution. And that's going to give us a new balance. There'll be a new equilibrium there. Whatever that point is, that's what we call osmotic pressure. And there's a formula for it, pi equals MRT. M, this is molarity. R, this is the gas constant. This is the same as the ideal gas constant that you learned about in the gas law. And T is the temperature that's going to be measured in Kelvin. So moles per liter, that's N for moles, volume for liters. Pressure, osmotic pressure, P is equal to N divided by V RT. Does that look familiar to anybody? It's PIV-NERD. That's right. We rearrange this. This is PV equals nRT. It's PIV-NERD. Right? It's the same kinds of ideas. If we have an ideal solution like this, right, we'll find osmotic pressure is going to behave mathematically the same way that we would expect ideal gases to behave. Lots of water purification systems use this principle. They do something that's called reverse osmosis, which really is kind of a dumb name if you think about it, because osmosis, as a definition, is going from low solid to high solid concentration. And reverse osmosis is just doing the reverse. So it's a way to kind of clean up the water. You want to get rid of the solutes and just end up with pure water. And all these purification systems do is they provide enough high pressure and a really, really fine membrane filter to basically force it to go the other way. They're going to provide enough pressure to offset the osmotic pressure and basically push this back in the other direction and get all the water back here on the left-hand side and leave all the red nasty particles that you don't want to drink on the right-hand side. And really what we're talking about a lot in this chapter is going to be volatility. Volatility is the ability to go from a liquid into a gas. The more volatile something is, the easier those molecules can transition from the liquid phase to the gas phase. When we're talking about these particles in solution, these solutes in solution that are causing osmosis in this case, these are going to be non-volatile particles. They cannot escape into the gas phase. Just a few more definitions that the textbook goes into. Hypertonic, hypotonic, and isotonic. This all has to do with the relative concentration of non-volatile solute particles when you're on one side of a membrane or the other side of a semi-permeable membrane. Now, in this case, the semi-permeable membrane is the cell membrane, right? So for all of you biology majors out there, cell membranes are semi-permeable membrane. In reverse osmosis, we're using a different kind of semi-permeable membrane. So on the left-hand side, we have some red blood cells, right? So when you use these terms, it's whatever's in the outside environment relative to the inside. So if you're hypertonic, that means you have more solute particles outside. So water is going to flow out to the area of higher solute concentration. And what that does is it kind of shrinks up the cells. On the right-hand side, it's hypotonic. That means you have more solute inside. So that means water is going to flow in. And when you have a nice balance, when you have the same concentration of solute particles on the inside of the cell versus the outside, then it's called isotonic. same concentration, both inside or outside. In other words, there's no net flow here. So in this case, if it's a hypotonic solution, we would say that the cells are in a hypotonic environment, or a hypertonic environment, or an isotonic environment. So the words themselves are easy. All you really have to remember is that it's the outside relative to the inside of which way it's going. Here's another example, same idea. How do you make a pickle? Here's a cucumber, all right? And we put it in a solution. We're gonna put it in a hypertonic solution that contains things like acetic acid and water. Vinegar is not a compound, it's a solution. It's a 5% acetic acid in water, okay? And when you put acetic acid in water, and we'll be doing this later on in the acids and bases chapter, you'll find that it makes some ions in solution. It makes the acetate ion, and it also makes hydrogen ions. But you also put, you put some salt in there, right? Yeah, so you put a lot of salt in there, what we call brine, which is just salt water. But basically, it's sodium ions and chloride ions. And there's other stuff in there as well, okay? There's other non-volatile solute particles in there, spices and whatnot. So what you end up with then is all of these charged particles, these ions that are non-volatile in the water, in the solution, in the hypertonic solution. So there's more non-volatile solute particles outside than there is inside. So the water is going to flow out of the cells, and that's going to end up shrinking the cucumber into a nice small pickle with other flavors in there as well. So there you go. It's the same idea, but it's not a cooking class. It's a chemistry class. Although, and a lot of times doing chemistry is a lot like cooking. And cooking is actually doing chemistry. There, think about that for a while. We talked about things being dissolved in solution. And we talked about how, like with sweet tea, that sugar, right, it's temperature dependent. The sugar will dissolve more readily when the solution is hot, right? Solubility of solids in liquid increases as the temperature increases. Just think about your sweet tea once again. Right? We make it with hot water, we don't make it with cold water. But now, think about your favorite carbonated beverage. You enjoy it cold. Why do you enjoy it cold? Does anyone like drinking hot soda? Why not? What's wrong with it? Besides that, it tastes nasty. That's the same thing as what you said. What happens to warm soda? Why don't you like warm soda? It's not because it tastes nasty. It's flat. What does that mean it's flat? It's less carbonated. It's lost the gas. So with sodas, this is a gas dissolved in water or dissolved in the liquid, okay? And in this case, it increases as the temperature decreases. It's reverse. Interesting. But you all have practical experience with that. So solid, temperature dependent, as it gets warmer, you get more solubilized. With a gas, you get more solubilized in the liquid as it gets colder. In fact, that's even shown at this graph down here below. Here's the solubility. So how many moles of a gas can we get dissolved per liter? All right, this is moles of a gas dissolved per liter of solution. And here's our temperature. And you can see that as the temperature decreases, we get more of the gas solubilized in the soda. What is the gas? It's just carbon dioxide. All right, so now we know what happens when it gets warm. So what's the first thing that happens when you open up that bottle? You hear a psh, right? That's because there's also a pressure dependency. The pressure of the gas above the liquid also plays a role. So we've got pressure of the gas above the liquid, and we have the temperature of the liquid. Both of these play a role as to how much gas can you get dissolved in a solution. The temperature we just talked about. The pressure of a gas above a liquid, that's what Henry's law is telling us about. Now, you know this product very well, so you know that there's gas dissolved in here, but you can't see it right now. Of course, if I shake this up real hard, you can see that there's some bubbles now coming up on the top, right? That's the gas coming out of the solution. Now, why did that happen? Because I shook it up, right? But what am I doing when I'm shaking it up? I'm giving those gas molecules more energy. And with more energy, they can escape from the liquid phase into the gas phase. But I haven't opened this up yet, so there's no place for that gas to go. So as I sit here and hold it while I'm talking, these gas bubbles are going to slowly go back into the solution. There's an equilibrium here, and I'll describe that in a moment. Okay, but we're keeping it capped. So this is under pressure and the gas isn't going anywhere. I just shook it to give the gas more energy to come out of the liquid. But as I put it down here and settle down, those bubbles will go away, but it's because the gas is now going back into the solution. It's reestablishing that equilibrium. So why does your soda go flat? And there's two reasons. We just talked about temperature is one of them. Because if I were to open up that bottle right now and pour it into a glass and come back in an hour, the temperature of that solution will have gone up. And that's what this graph is showing you. As the temperature increases, so as we go from, say, 4 degrees, as the temperature, now here, I'll draw my arrow in the other way. As the temperature warms up over time, less and less. So here's how much carbon dioxide was dissolved when it was cold. As it warms up, now we have less that's dissolved because of this temperature dependency. This is actually a relatively small contribution. Most of the reason that the soda goes flat over time is due to Henry's law. And that's because the pressure of the gas above the liquid has changed. And what does that mean? Pressure of the gas above the liquid. All right, so here's our liquid solution. This is CO2 gas that's dissolved in aqueous solution. Let's just say it's dissolved in the liquid here. Now, what's keeping it in that solution? Why doesn't the gas just fly away? The atmosphere. There's still pressure in the atmosphere. Now, there's also temperature. The colder that solution gets, the more gas we can dissolve. But what's keeping it in that solution is that there's a pressure of carbon dioxide gas above the liquid. Remember, the pressure of the atmosphere is, remember Dalton's law of partial pressures that we talked about? If we say that this is 1 atmosphere, that's a combination of the partial pressure due to nitrogen gas. That's about 78% nitrogen. So that would be 0.078 atmosphere. And there's the partial pressure coming from the oxygen gas in the atmosphere. That's about 21%. This would be about 0.21 atmospheres, and so on and so forth. And then way down the list here, far less than 1%, we have the partial pressure of carbon dioxide, right? It's much less than 1%. Now, in the case of our soda that we've just poured into a glass, ready to enjoy, but we had to walk away and go to the grocery store because we forgot our chips and salsa. We come back an hour later and it's gone flat. Not because it's warmed up, but because of the partial pressure of carbon dioxide above the liquid. So even though we have nitrogen gas and oxygen gas at much higher pressure above the liquid, it's only the partial pressure of carbon dioxide that dictates how much we can keep in that solution. But remember that there is an equilibrium. There's always an equilibrium here. So the equilibrium in this case is between the gas particles that happen to escape into the gas phase, so out of the liquid, but they're counterbalanced by, because of the partial pressure of the carbon dioxide gas above the liquid, that's basically pushing them back into becoming solubilized in the solution. So even if we forget about the temperature dependency of it, we can influence how much gas is dissolved by changing the partial pressure above the liquid. That's what Henry's law is telling us. In Henry's law, it's a very simple proportion. It's simply the molarity of the gas that's dissolved, okay? Molarity of the gas dissolved. Let's just call that M, capital M, just for molarity. It's going to be moles per liter. It's moles of gas per liter of solution, it's going to be dependent on two things. It's going to be dependent on the partial pressure of the gas above the liquid. I'm going to write that in a minute. And then there's also a proportionality constant. I'm going to write that first. It's K times P. K is just going to be a solubility constant. It will tell us how many moles of gas we can dissolve per liter per 1 atmosphere pressure. So for every 1 atmosphere of pressure, we should be able to get so many moles of gas into so many liters of the solution. That's what the solubility constant is telling us. There will be a different value for every gas. Carbon dioxide has its own value. Oxygen gas has its own value, and so on and so forth. P, pressure, this is the partial pressure of that particular gas above the liquid. Okay, that's all that's involved here. So mathematically speaking, all you need to know is what the solubility constant is and what the partial pressure is, and you'll be able to tell how many moles of gas you can get dissolved into the liquid. Again, that's removing the temperature aspect of it. We're not going to do any calculations with the temperature aspect of it. So let's take our unopened bottle of soda. Here it is. It's packaged under a pressure of about 6 atmospheres, partial pressure of carbon dioxide, which is pretty high. That's why when we open it up, the first thing we're going to hear is, psh. Of course, I don't want to do that now because then it's going to start to go flat. And we're going to understand why that is in a moment. But let me just diagram this for you. Let's cap it. All right, so there's my Diet Pepsi. Okay, so we have a partial pressure of carbon dioxide in here. I said it's about 6 atmospheres. So let's say it is 6 atmosphere. That's really high, considering that atmospheric pressure at sea level is only 1 atmosphere, and that's of everything. That's all the nitrogen, the oxygen, whatnot. Okay, so this is pretty high, 6 atmosphere of carbon dioxide. But there's still an equilibrium established here, right? If I were to write in, once again, our little balls of carbon dioxide gas all throughout here, there is that equilibrium that's established. We have a little bit that can escape into the gas phase, but it's counterbalanced by the same number of gas molecules that get re-dissolved in the liquid. So that's our equilibrium. So we can actually calculate what is the molarity of gas that's dissolved in the liquid when the partial pressure is 6 atmosphere. All we're missing is that proportionality, that solubility constant. Well, here it's given to you. So for carbon dioxide gas, here's the solubility constant. This tells us that, again, temperature aside, this tells us that for every liter of solution at 1 atmosphere, we can get 3.1 times 10 to the minus 2 moles of carbon dioxide gas dissolved. That's what that number is telling us. So let's calculate what our molarity is when it's capped. The molarity is going to be equal to our proportionality constant, 3.1 times, or sorry, our solubility constant, it's the same thing. 3.1 times 10 to the minus second moles of carbon dioxide will be dissolved for every 1 liter at every 1 atmosphere. And what is our partial pressure? Well, our partial pressure now is 6.0 atmospheres, right? So this is K, and this is our partial pressure of carbon dioxide. And when we do that math, we get 0.19 moles of carbon dioxide dissolved in the liquid per 1 liter of the liquid. And you can see the units cancel out. Atmosphere cancels with atmosphere, and we end up with moles per liter. Moles per liter, that's the units of molarity, right? Now, remember, I told you that the percentage partial pressure of carbon dioxide in the atmosphere is much less than 1%. This is like 3.1% if it were coming from a mixture for 1 atmosphere of atmospheric gases. Okay, so this is actually a pretty high number. Now, let's take a look at what happens when we open up the soda. As soon as you open it up, you hear that initial psh, but then you don't keep hearing gases escaping. That initial psh is nothing to do with the gas that's in the solution. That initial fizz is just the equalization of the 6 atmosphere partial pressure of carbon dioxide here with the partial pressure of carbon dioxide in the atmosphere, which is very, very low. Okay, so when we open this and we hear our big psh, that noise is really coming just from the pressure equalizing with the atmospheric pressure. I know it seems confusing because I say atmospheric pressure, but our units are atmospheres. So that's why I'm being very careful to say atmospheric pressure. And remember that the partial pressure of carbon dioxide in the atmosphere is very, very, very low. In fact, I should tell you that the partial pressure of carbon dioxide in the atmosphere or in air is approximately 5.0 times 10 to the minus fourth atmosphere. Much, much lower than it is bottled out of the company at 3 times 10 to the minus, at 6 atmosphere. 6 versus 5.0 times 10 to the minus fourth. That's a huge difference. This number is 0.0005 atmosphere versus 6.0 when capped. So that's a huge difference, okay? And in fact, we can calculate, well, what will the new molarity be of the solution once everything has equilibrated to atmospheric above the liquid? So we can make that calculation too. Once it's open, the new molarity, well, the solubility constant is still the same. That just tells us how many moles we can get solubilized per liter per atmosphere. But now we have a new partial pressure above the liquid. Now it's going to be 5 times 10 to the minus fourth atmosphere. So we should expect to get a lot less solubilized. This number comes out to be 1.6 times 10 to the minus fifth moles of carbon dioxide per liter. That's when opened. That's a lot less, okay? It's going to establish a new equilibrium because there's still going to be gas particles escaping, but they're still going to be pushed down by the partial pressure of carbon dioxide. But now it's just going to be a lot less partial pressure on top. And it takes time for that new equilibrium to be established. That's why, but if this were actually in an open glass, throughout the entire lecture, you would see bubbles continuing to come out of the solution of gas going into the gas phase, okay? So dissolved gas going into the gas phase. And that will keep on happening because what we've done is now that we've changed the partial pressure of carbon dioxide above the liquid, this new equilibrium is being established. And as it's going towards that new equilibrium, we're slowly getting more and more gas coming out of the solution. But it's not all at once. It takes time. And during that time, right, in your glass, you're still going to see a few bubbles will always be coming out because we're establishing a new equilibrium due to this change in partial pressure. But if you wait long enough, you come back, now that new equilibrium has been established and you have a whole lot less carbon dioxide in the liquid, and so you drink the soda and it tastes flat.